Okay. Okay, good. So we are back. So what we'll do is we're gonna go how to process text. Then we're gonna learn something called an embedding. I guess you've heard many times in this course what's an embedding, but this has become like one of the most important concept in the yeah in the whole machine learning community. And then we will discuss on the backbone of the DGT, which is the transformer, how exactly transformer works. And then from there, we're going to go to a part of transformer that's used in GPT, which is decoder. And then that would basically take us to the end of the class, going over LLMs, how to actually think of LLMs. Okay, so this will be a bit longer, but let's try to go at least the first part a bit more fast. Okay, so usually, let's say when we think about text, you can immediately think about, let's say, two types of task. One is through your mail. We get tons of spam mails in Zimbra. So yeah, you have won $1 million prize, or somebody wants to give you because they're dying. So somebody from Germany or Nigeria thought that you were the owner of this. So that's a spam mail. So that should immediately be binned in the spam. So just from the text, I don't know how, but this automatic processor should learn this. The other one is something like, let's say, what you use a lot, something like, let's say, going to Amazon or whatever marketplace, and then you want to see the review. So how good was the product? Or you can also go to IMDb to see the movie rating. Okay, how good was the movie, etc. So these are usually the sentiment analysis or product review analysis. You give it automatically a 5 star or 4 star, some number, or the movie was good, bad, how much do you rate out of 10? So those two automatically comes into mind. So this should be, let's say, the kind of common task with text, what we would do maybe even, let's say, 10 years back. This is not what we do now. We know what we do. We use ChatGPT, okay? So we will see how ChatGPT got so good. So to go there, we have to go in step by step. So now you see the trouble is that we started from text. This is actually a big difference on how we think about, let's say, images. So images, when we think about images, it already contains numbers. So the pixel values already contain some numbers. So we can think about this as like as a 2D grid or 3D grid. So this is copied from second class whole slides. So this is basically, let's say, a 2D grid. It has some numbers, 1 and 0, and then I pass it to the computer. So first thing that should come to your mind is that how can I make those text processable via some numbers, okay? So we discussed this. So let's say we can go on this array, like a pixel value of 0 and 1. We basically create an NumPy array of 2D, two dimension, and then we just pass it. We can have continuous number, some number between 0 to 255. So that would be a grayscale image. So this we know, and we could have some color image. Instead of just only one channel, we could have three different channels. And then basically pixels are just an array of numbers, and then we pass it through the network, and then it does something. So that is the big difference from image perspective, is that whatever image you take, it already contains some raw number data. But text is text, it doesn't have any number. So first, somehow we have to turn it into some numbers. So how do we think about having a numerical representation of the text? Okay. Now, by the way, this will appear again and again, but just to start from the beginning. So when we think about text, you can think about it's like as like a time series. Okay. So as I am speaking, blah blah blah. So these are all related with time. So I'm speaking over time. So when time equals to 0, 1, 2, 3, this will continue. Okay. Now, this is directly comparable to some other time series, something like let's say the stock market prediction. So we have price, uh, the days and price. And then we can plot S&P, and then we can plot Nasdaq. Okay. So whenever you think about text, you can always think about as something that happens over time. Okay. So we could already think about this as a time series. So of course, for stocks, this is again another 1D array, but this is just numbers. So processing, let's say, a series of stock market values over 5 years or 10 years, way easy because these are already some numbers. $5,000, $4,000, blah, blah. But now you're back to text again. Think about this as you are speaking as like something that's evolving over time. Okay, so now let's say we have this sample text. So this is a sample text. So what we do is first we break it down to some smaller units. We call them token. Okay, I guess you should know the word because this is becoming the new concept, token. Okay, so one of the simple ways to break is just break it by the space. Whenever I have a space in the sentence, I just make a split there. So this is a sample text. These are down 1, 2, 3, 4, 5 different units. But these are still different units, so I have to assign them some numbers. So now you might think, okay, what you said is okay, great. So we can break it down into some small words. But why don't we break it down to some characters? So A, B, C, D, E, F, G, H, and then it goes to A to Z, and some other hash, exclamation mark, and that should be enough. What we will focus on is something called a subword, and why we want to go to subword. So let's go there. We are still stuck in text. We have to go from text to number. Okay, so let's see. So let's say I have a big book. Okay, so the big book has only 3 sentences. Okay, this is a joke. So this big book that I want to process through my computer has only 3 sentences. The cat runs, the cat jumps, and the dog jumps. Okay. We in machine learning we call this big book, or let's say the whole internet, as my corpus. So in this case, my corpus is only 3 sentences. You can take the whole internet data, and that will be your whole internet corpus. So that's a ML terminology. Then what we want to do is we go from token to create something called a vocabulary. So this will be used by the model. So vocabulary you can think of as consisting of unique tokens mapped to some integers. Okay, so you're going to see some examples very soon. So first, let's say I break it down via the space. So this is just one line Python. So I make everything in lowercase, and then I break it down in via space. So now I have this different words. So how do I go from words to integer? Okay. So now let's say I assign every word as a unique integer. So now you see that, okay, so D is assigned 1. So whenever D appears, I basically put 1. So cat is assigned 2, and then runs assigned 4. And whenever this repeats, we know exactly what's happening. So this is now my whole vocabulary. And I needed 6 integers, okay? So now you can think that if I, instead of this 3 lines, if I have the whole, really the, let's say the whole National Library book or internet data, of course, the vocabulary size will increase because then we need way more unique tokens to represent. So first we went from text to numbers. Then we decided that unique numbers can be represented as vocabulary. So let's say now next time whenever I see cat in another sentence, I can automatically assign that token 2. So that's my whole vocabulary. Okay, so this 6, this dot, the full stop, I have to somehow assign when the sentence ends. That's in my language, it's a full stop in English language or whatever language. You put, let's say, a bar or a full stop. So that has to be also assigned. So that got a number 6. Basically, now we have our vocabulary. So Yeah. So now as we go increase the data sets, the vocabulary will increase tremendously. There are some other stuffs. So let's say if I train a neural net with only these three sentences, and now suddenly I see a pigeon that flies. So pigeon doesn't exist in this corpus. So I call this. It's usually in the book. It's written as something like this: OOV, out of vocabulary. Okay. So this will be assigned to a different token. I don't know, 9. So pigeon will get a 9, horse will get a 9, everything that doesn't exist in the vocabulary, all will be assigned to the same token. Okay? So that's why it's better to have a larger vocabulary so that I don't have this weird same integer assigned to all the out of vocabulary tokens. Okay? Okay, so what about we make it short? Instead of going to vocabulary, we can go to characters. So this is what I was telling. Then I have only 26 numbers, right? A, B, C, D. And that's it, 26. And then whatever, full stop, exclamation mark, I don't know what you write. Let's say the inverted comma, some other tokens. That's it. I probably need only 50 tokens, 50 unique integers. And now I can represent the whole English language. Why we don't do that? Yeah, I guess you know why we don't do that, because that will have no contextual meaning. So let's say I have a cat and I have a mat. So cat got a token, let's say 2, 4, 5. This is 3, 4, 5. Now, of course, this 4 and 5 here in this cat and 4 and 5 here in mat, they represent completely different things. So no contextual meaning. They have same numbers, but no contextual meaning. Okay? We don't want that. The other part is that if I have big sentences, then I need humongous amount of these numbers. That's also not good. Okay, so let's say before what we did is something like break it by space. So that we call word-based token. The other one is character-based token. So we could do something like this, okay? Now we kind of understand that maybe both are not so good. You can still argue that maybe word-based tokenizer is still good, but you will see why word-based tokenizer is still not so efficient. It is good, but it's not so efficient. So what we want to do, we want to go somewhere in between. So let's think about an example. So let's say we have this unique words in my vocabulary. So let's say I downloaded a book and then I have this word. So low, lower, what do you have? No, we don't have lower. Okay, so low, highest, lowest, higher, etc. Okay, now this vocabulary doesn't have this word lower, but it has the word higher and newer. It also has low. Okay, it's actually now possible if I can break it down to low and R, then I can break the down, let's say this higher to high and R. And now I have a representation for the word lower that didn't exist in my vocabulary. So that's why we do it by a sub-word. So I had the whole word higher, I broke it down to high and R. And then now suddenly I have this new word lower that didn't exist in my vocabulary. Now I could assign specific tokens that would carry similar meaning to higher. This is what we use. We have another example, very cool. You can think about the different verb formats. So let's say learning, learned, learned. It all stems from the word learn. So if I have seen some other verb format, like let's say sleep. From sleep, we go to slept. Right? Then cat, then cat goes to caught, and etc. etc. Okay? Cat goes to catching. So I can break that down, this learning to learn and in, and then I have cat goes to catch in. So I don't, even if I don't have a word catching in my vocabulary, if I have the verb catch, I should be able to form what exactly catching means. So this is what is done in GPT. It's called the byte pair encoding. This is a beautiful algorithm. You can just search on Wikipedia. The Wikipedia explanation is amazing. It's probably the best explanation, better than the original paper. Okay? That's why sometimes Wikipedia is good. Okay, so all of them. So I don't know actually what is done in 5, but at least still when OpenAI was open till the version 4.0, we actually at least get to know what they did. But now we have no clue what they do. So at least till then, they used byte pair encoding algorithm. That's basically breaking down the words into subwords. Okay, this is like finding a balance. So we have possible way of reducing this out of vocabulary option by breaking it down to subwords. And then also, even if the sequence increases, so let's say I give a huge prompt with no full stop, no comma, it's a huge sentence, okay? If you look back to some old texts like some Iliad and Odyssey, Homer, they have like a huge chunk of paragraph without any comma or full stop. So it's like you have to read the whole paragraph. So imagine processing that whole paragraph. But we could break it down with subwords and we're going to require less and less tokens. One example from GPT-2 is, let's say, for the vocabulary size. So you can think of this as like a dictionary. So you could think of your vocabulary as your dictionary. So this has about 57K vocabulary. You already think about this when I mention vocabulary, you think about this as tokens. So think about this as tokens. Yes. So now we have these tokens. Great. So now we have some numbers to represent text. Let's just pass it through the net. So we have the text, we represent it by a number, and then we pass it through the network. Now we want to do some sentiment analysis, okay? Whether the movie was good or bad, it's a positive or negative. So just a, let's say a simple classification. I want to give a 0 or 1. Now there is another problem. The problem is, so let's say I have these 3 different uh, review. So one is this movie was good, this movie was bad, this movie was great. So both of them, the good and great, both should be assigned positive, and bad is assigned negative. But good and great, they're kind of similar. So how do I know that good and great are similar and bad is very far away from both good and great? They all have different unique numbers. But how do I make those numbers close by, good and great? If I just randomly assign numbers, that's not a good idea. Somehow, when we speak, we have to think about semantics. Can we actually capture that good and great are close by? I give a neural net a lot of text. It should be able to understand at some point. Okay, good, great, greater, greatest, they should somehow combine together. And bad, worst, they will combine in another way. They are bad. How do I know this? How do I make those numbers close by? So here comes this beautiful concept of embedding. So before I go to embedding, I must discuss how it was done before. And that was very terrible way. I actually don't know how it worked because I didn't use any, let's say from, I started working from 2018 on ML. So I never used how one-hot encoding was actually used for processing text because this is a terrible idea. So how it was done before embedding. So one-hot encoding is every word gets a unique vector, okay? And the vector size is the length of the vocabulary. So how does that work? So let's say I had this movie was good, this movie was bad, this movie was great, okay? So if I have only these 3 sentences, then this is my vocabulary. That's my whole dictionary, okay? So I haven't given network any kind of extent of only this treating. So now there will be 3 sentences. My vocabulary size is 6. So every vector, every token, or every word, this movie was good, bad, great, whatever. All of this token will have length of 6. Okay, so that's what you're seeing here. And one-hot encoding, this when this matches with this, it will get 1. When movie matches with movie, it will get 1. Everything else is 0. So only the diagonal will have 1 and everything else is 0. So this is one hot encoding. Only one is hot. So only one flag is up. That's what it means. What is the problem with this? Can you make a guess? What is the problem with this? Why we don't want this? Any idea? We could process text like this. So if we process text like this, it should go something like this. Okay. So now my sentence looks like this. This movie was good. Okay.
Sorry.
The length?
Yes, it will become big, very big, expand.
How? Which one? Which one will become? So you're thinking about the sentence or the vectors?
Vectors.
The vectors itself, they will become big. And the other problem is that these vectors in ML, we call them sparse because there is only one information and that is this one. Everything else is 0. So with this too many zeros, we are basically filling up a large chunk of memory that doesn't signify any other meaning. It's basically like, if you think of this as like a pointer points on the first entry here. Here is the second entry, and so on and so on. Do I need the other pointers at all? Maybe I need, but if all of them are 0, they probably doesn't convey a lot of meaning. So I could actually pass through this network. Yeah? So I have 3 sentences. I pass it through the network. Maybe it works. Actually, it used to work. It's very surprising to me how it actually worked. Because after you see embedding, it would be very difficult to believe that this thing actually worked. Okay, so first thing, yes, go. We will come to this. Okay. Okay. Very good point. Very good point. Okay. Yeah. When we write on ChatGPT, yeah, most of the times it's freely type. We don't even care. We are so rude to ChatGPT. We just assume that it will understand. Okay. We'll come to this. But embedding is a way to think about this. Okay. So first thing, the big problem with this one hot encoding is what Miha said, is that it's a huge waste of memory. So as my vocabulary increases, so let's say in GPT-2, GPT-2 was a very detailed paper. So you know exactly how to reproduce GPT-2. If you start now, take a 1 week break, you could actually reproduce GPT-2 with some help from ChatGPT and Gemini. So we have 57K vocabulary in GPT-2. So imagine that. So let's say I have this word, this. So this will be something like this. So this is, let's say the first entry is 1 that represents this. And now I have 57 minus k minus 1. Okay. This is ridiculous. Okay. And this will happen for all other words. One flag will be 1 and everything else is 0. This is a huge waste of memory. We probably wouldn't like to do this. Okay. The other one, now we are back to a big problem is that, so let's say we have this good. So good vector is, I don't know. So let's say 0, 1, 0. Okay, so now I have great. Okay, so this is 0, 0, 1. Now I have bad. Let's say this is 1, 0, 0. How do I know that this good is close to great? And good and great are very far away from bad. Now you start to think in terms of vectors. If I take a dot product, both of these are 0 because this 0 will multiply with 0, 1 will multiply with 0, 0 will multiply with 1, 0. No context, no nothing. I will never be able to recover contextual meaning that good is close to great and bad lies far away. So now we can go to embedding. Why we need embedding and why one hot encoding is not good. So embedding, we think of this as a way to understand semantics in the words. So good is close to great, okay? So let's see an example. So let's say, irrespective of these 2 different sentences, the meaning is the same. So let's read the first one. So let's say Sarah entered the old library. Her heart was racing. She knew something was hidden behind the dusty blah, blah, blah. Sarah entered into the ancient library. Her heart was pounding. She sensed something was concealed behind the dusty. So they basically say the same thing, but if I give ChatGPT these 2 things, it should automatically recognize that old and ancient basically convey the same thing. New, knowing and sensing, somehow semantically similar. Hidden and concealed are somehow semantically similar. It should be able to predict. It could be hidden behind the books, could be hidden behind the shelves, table, etc. This would be very difficult with one-hot encoding because old will have a one-hot vector, ancient will have a separate one-hot vector. If I take a dot product, they're not close by. They're just simple zero, okay? Because this is one-hot encoding. Embedding is to represent things in a dense vector. So what does a dense vector means? One-hot vector is sparse. They have many zeros or only one. Dense is I define a particular size. So this is defined by me. This is chosen by me. What's the dimension of this vector? Let's say I define a 10-dimensional vector, and the words will be represented, corresponding different words will have different floating point number for these 10 entries. All of the words will be represented by 10 different numbers, floating point numbers. I guess now you can make a guess already that let's say if I take a dot product of these two vectors, if this is good and great, maybe they point in the same direction because that's what we want. We want the model to understand semantic meaning. So this is very different from one-hot encoding. When two vectors are similar, and by similar, what we mean is that maybe the numbers are close by, so that when we take the dot product, they kind of point in the same direction. This paper was published by Google, and now it has reached 52,000 citations. You're going to see some ridiculous number of citations later on, okay? 52,000 citations? Yeah, this is crazy, okay? But you're going to see some crazy number later on. Pivotal paper. So 2013 it came out. Yeah, so imagine, I don't know how actually people did before 2013. So of course I started 2017, 18, so of course we all used embedding. So what's the idea? So the idea is that somehow if I have these two dense vectors, king and queen, they should point in the same direction and that should be separate from cat. Now, of course, I said that, okay, this vector is 10D. Yeah, but I cannot show you 10D. So I'm just showing you 2D, okay? This is just representation. The idea is that these dimensions, so let's say this 10 dimension on that previous vector, they probably represent something. I don't know. Maybe they represent age, maybe they represent wealth, maybe they represent something, I don't know. So let's take an example. Let's think about that these two axes represent royalty and age. So these two dimensions, they are royalty and age. So now, of course, king and queen, let's say reasonable age, but the royalty is way higher than a normal man and woman. And that's the idea of finding semantic meaning, that man and woman are close by, king and queen are close by, but it differs by royalty, okay? If we think about gender, let's say now I have a 3D vector, okay? Because it's 10D, so it's shown 2D. And now I have a 3D vector. I should expect that at some point, queen and woman should be close by, and king and woman, king and man should be close by. If I have another direction that represents gender. So with this, now I have this dense representation. This is my embedding matrix, okay? So how do we define the size of the embedding matrix? It depends on the how many dimension of embedding I chose. So let's say here I chose, I don't know, 1, 2, 3, 4, 5. Gender, wealth, royalty, weight, and speak. Okay? This is what I'm assuming. Maybe the model learns like this. I don't know if it will learn like this or not. So let's say these are my 5-dimensional embedding. What's the size of the embedding? We will see later on. So size depends on the choice of the dimension, that 5, and the number of tokens that I'm giving into the model. Okay? So with this, what I'm expecting that it should follow some vector rules, simple vector rules. So if I take this example, this dense matrix, and if I do some simple vector calculation, so king minus man, and I add woman, What do you think the result is? King minus man plus 1. What is that? What this should equal? Queen. It should not be cat, okay? Okay. So that's what happens. So it's 0.8, it's close to 0.7. That's what we mean that by semantically close by. It's not that it will be exactly same, but somehow it learned the representation. This is very, very cool. When we train a network, we could visualize something like this. You could go any website and find something like this. Let's say king, this is so blurry. Sorry. King, man and woman, banana, orange and apple, basketball, football, golf, dog, cat, others, okay? Semantically similar words should group together. This is very important, that we somehow understand what the word they actually are conveying. If I understand the word, then I can understand the sentences. Okay, so embedding matrix would be like a lookup table. So I get a corresponding token and I find the corresponding embedding vector. So what does that mean? So I find in my training data a word key, and this is my embedding vector 0.81. Okay. Okay. So usually, so let's say this length of vector could be 4,000 dimensions. You're going to see some real numbers soon, what actually used in GPT-2 and GPT-3, etc. How does it work? Yeah, so that's basically work as like a lookup table. So let's say I get this word key. The key has a token 768. I get the corresponding embedded vector, whatever dimension it is. By the way, I showed you this as a square matrix. This doesn't need to be square matrix. 99.999% of the time, it's not a square matrix. Okay? So here it's 768 by 768. Doesn't need to be. It could be 768 by 1 million. Okay? So for that corresponding token, 768, that represents the word key, I have that corresponding embedding vector. Okay? Yeah. So for GPT-2, our vocabulary size was 57,000. Yes, our vocabulary size was 57,000 and embedding dimension was 768. Now then we go to Llama, a bit more advanced, came a bit later. And of course, we now have version 3, way bigger. We don't know what's happening there. 120K vocabulary and 4,000 embedding dimension. Okay, so the way it works, we randomly initialize some floating point number between 0 and 1, and then we train the model. This embedding matrix is a learned matrix. We just define the dimension, let's say 50K times 768, and then we just let it learn. What would be those numbers? I give a huge number of text. You're going to see how it learns, etc. in context of transformer. It will come soon. So I don't know how many of you use this anymore. This is for the boomers, okay, like me. For us, we used to have Stack Overflow, okay? It used to exist. It doesn't exist anymore. It's dead silent, okay? So I was taking I wrote an answer explaining with example how embedding works in 2019, okay? Even though it's not so far, I mean, if I close my eyes, I can visualize 2019 very easily. But in context of AI, it's like I feel like yeah, I'm dead and I'm born again. Okay, I can't believe how like 6 years. I can't believe. Oh my God, 7 years. It feels like 70 years. Okay, so this is embedding. Any question with embedding? Because if you don't understand embedding, then transformer will not work. It's okay? Okay. So now we're going to go to transformer. Once we understand embedding, we are ready for transformer. Transformer is basically some vector operation. Basically matrix multiplication. The whole LLM is essentially some matrix multiplication. So that's what we will try to visualize, okay? We will try to visualize how transformer works. Not this one. This is not matrix multiplication. This one is matrix multiplication, okay? And that transformer is way more useful than this one. Okay, so this network is a bit of a mess. Okay, so we will try to break it down. What the hell is going on? So this is the paper when it was introduced. By the way, I said I started, let's say 2017, 18. I didn't know the paper till 2019 because this paper was buried inside until ChatGPT-2 released the GPT-2 paper. And then something happened, okay? So when you search on Google, this paper now has 250,000 citation, okay? I think this will be the paper that will reach 1 million citation in my lifetime. Imagine a paper that reaches 1 million citation. So yeah, cry. Yeah, I'm not crying. I'm happy. Okay, because we can all be humble. Okay, this will not be possible by any other thing. Okay, so whenever somebody mentions the number of citations, okay, you have a good reference. So we want to go from semantic to something different. Okay, and that is contextual understanding. So semantic is great. So let's say apple, orange, and banana are falling close by because the network learned that they are fruits. But now suddenly I have a sentence that says Apple released a new iPhone. Now, if I have the same embedding vector that was used for defining the fruit, yeah, then basically this sentence means that, okay, I don't know what it means. If this apple means fruit, they have big trouble. It will not work, okay? So now we want to go from semantics to contextual understanding. This is the big achievement by Transformer. How can we understand a word in the form of a context? So given a context, I want to understand what does actually Apple refers. I should be able to immediately recognize that this should fall in the direction of Samsung, Xiaomi, or whatever, LG, whatever, okay? And this is not the fruit. So how it used to work before, without the contextual embedding, I'm gonna get a same embedding vector. Apple released the phone, or she ate a red apple, they're gonna get the same vector. Not good. We don't want that. So what we want is to somehow relate it to other words in the sentence. Okay. If you don't want to listen to transformer, just remember this diagram, how it's actually done. So we start off with some sentence, we go from sentence to subwords, we tokenize the subwords, then we reach to an embedding matrix, okay? This embedding matrix is learned, it's predefined dimension. This captures the semantic meaning. It's not good enough. Now, what transformer does, it gives contextual meaning. So we're going to understand how it actually captures this contextual meaning, okay? So the most important concept here is something called the self-attention. So that's the paper. Attention is all you need. So we want to understand how attention actually works. So the idea is that if you let's say write a prompt on ChatGPT, the idea is that ChatGPT should see through the whole prompt. So let's say you give a code, okay? So def, I don't know, find meaning, okay? You wrote a game. You give some coordinates, some position, and then your function. You give the whole code to ChatGPT from your Python file, copy paste this. The idea is that ChatGPT should be able to infer this from this whole context. Okay, the whole code should be understandable at the same time. What we used to do before. So let's say when I was working in 2019, mostly I didn't know transformer. So we used to have something called a recurrent network. So let's say we can go back to let's say this I8 atom. So a network will process something like this. I goes to the network. Okay, then comes 8, goes to the network. Then comes apple that goes to the network. Okay, one by one. The idea of the self-attention is that it takes in the whole context. Whatever prompt you gave, the whole sentence goes in, and then it will try to understand. So before we used to have, let's say, this recurrent neural net, and let's say we have these two sentences, okay? Dog bites man. and man bites dog, okay? So you understand that the sentences, or when we speak, again, language models are basically time series. Okay, dog bites man. Okay, man bites dog. Whoa, what the hell is going on here? Okay, okay. So how do we actually let the model know that which word comes at what position? And depending on the position, they might mean something completely different. The ChatGPT should know that when you write that, okay, your GPT, I saw a dog is biting a man. ChatGPT might suggest something. Okay, when you write ChatGPT, your GPT, I saw a man biting a dog. Okay, it should call police. So the idea is that before we go to the context, somehow we should be aware of this position, and that comes in the network via this positional encoding. So we discussed after this. We have our embedding matrix ready, okay? Embedding matrix captures the semantics. Now we want to go to positional encoding. Then we're gonna capture this contextual embedding via self-attention. So let's go to positional embedding, very easy, the simple vector operation. So, okay. How do you think we should think about this positional encoding? What, let's say, let's make some guess. What could be a requirement for positional encoding? How can I encode position? So let's say I ate apple, apple ate me. Okay. So how do I make some requirements for this vector? This will be another vector. Okay. So what would be some suggestions? How can I give this to the network? No. Think about position. So forget about semantics and meanings. Just think about position. I ate apple and apple ate me. Okay.
You can assign a position as a number to each word.
Yes.
You can assign a position like relative from 0 to 1 in a sentence, or you can do something else.
That's right. That's right. So the first one is the one that we want to proceed by. The reason we want to proceed like this is because irrespective of the sentence, irrespective of the meaning, okay, whatever is in here, all of these positions, let's say it's divided by subwords, corresponding subwords has some tokens, I don't know, 100, 59, 23, blah, 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 corresponding token, they should have exact same position vector. So the first one that occurs maybe gets, I don't know, 0.2. Second one should be 0.4. It doesn't matter. The sentence, the position, these numbers should be the same, irrespective of sentence. It should depend only on the position, okay? Every position should get the same identifier. So that's how it was introduced in the paper. Okay, so in the original transformer paper, they just used a predefined positional embedding. That's called the sinusoidal embedding. Forget about this. You can think about this as just assigning some particular number between 0 and 1, some very small number. So let's say I have this, queen and king. So I have a corresponding token. I look at the corresponding embedding for the token for queen. I get this, corresponding for and, corresponding for king. Those are the green ones are my corresponding embeddings. And I just add corresponding tokenizer, okay? So positional encoding. So what you see here, they're just slightly different because this was how it was introduced in the transformer paper. It was sinusoidal embedding, okay? So the idea is that let's say I have a war sentence, queen and king. So I have a sentence, queen and king, and I have another sentence, king and queen. Okay, so when I go to king and queen, this king vector, whatever that vector, should be added with this same positional encoding. Okay, so positional encoding is the corresponding vector representing a particular position.
So basically, to every word in the text, we are assigning a vector or matrix with dimensions 2 multiplied by the size of this vector, and one column of this matrix corresponds to semantic meaning in
Yes.
the corpus, and the second to the position in this text.
That's right. That's right. That's right. Think about this as we have, you're going to see some more visuals later on. Think about this like we have a sentence, we go to tokenizer, get the corresponding embedding, and then we just add the corresponding positional embedding. We have a lookup table for every word. That is my embedding table. I get to the embedding table, I add the corresponding positional vector. With that, somehow I told the network that which one comes at what position. This is very important because in self-attention, did I mention it? This one. When it processes the data, it processes everything together. There is no ordering. So inherently in self-attention, there is no mention of ordering. So it will process the whole text simultaneously, and you can reshuffle the word and etc., etc. So we must somehow assign this positional encoding because we know that languages have some sort of inherent time series nature. Okay. So we discussed embedding, positional encoding. Now we're going to go to attention. So attention is basically described in this two paragraphs and that equation. So what it says is that, okay, we have this key and vector, values, and then we have this corresponding dimensions for those vectors, dk and dv, okay? And then we have this very famous equation, the attention matrix equation, okay? It's something, I don't know, what is this, softmax, okay? We're gonna come back to this, what is this, okay? Let's see some example. Okay, so the idea is that, again, what we are trying to learn, given a sentence, given a big context, I want to learn every token, how it interacts with others. Because that's the idea, contextual understanding, okay? So, the idea here is that for every token in the input sequence, we're going to have a corresponding query, key and value vector. So how does that look like? It looks something like this. So let's say I have this queen and king. So let's say token A, token B, and token C. For every of the tokens, we have assigned a corresponding query, key, and value vector. Okay. Now for the dimension is the thing that you want to somehow get through your head, okay? Because this is where matrix multiplication comes in. So now you can really think of giving input text to a model, okay? So let's say I have given this input text X. That's a set of real integers back again. So those type of assignment, okay? That R is basically a set of real integers. So how it is? It's a matrix L times D model. Okay? So L is the length of your sequence. Okay? And D is the dimension of this embedding matrix. That's how it should be. Because if I go back, where did we start from? We are stuck in this embedding input. We are stuck in this embedding and positional encoding. And if we look back, the understanding of embedding was something like this. We had this embedding matrix. This is the size of the vocabulary, and this is the size of the embedding vector. So we think of it as like that. When we give an corresponding sentence, so it will depend on the dimension of the sentence, which is L, number of tokens in the sentence, times the embedding matrix dimension. That's the D model, okay? Now, how do we think about Q and K? We define this weight matrices. These are WQ and WK. If you forget about that equation, just think about this dimension of this weight matrix. It has this dimension, this embedding matrix dimension, D model, times dk. dk is the dimension of Q and K. So once we have this, So WQ multiplied with X. So X has this dimension D model, and let's say we have WQ D model multiplied with DK. We're gonna get back, if I multiply this, of course, this will go away with the matrix multiplication, and I'm gonna have L times dk. This is the dimension of Q and K, both. Both of them have dimension dk. So just think about this as a form of matrix, okay? We're gonna be stuck with this matrix multiplication for coming 15 minutes. So how do we think about this properly? So let's say I have corresponding token A and token B, and I want to find interaction in token A and token B. I have corresponding vectors assigned to token A and token B, query, key, and value. Query is basically trying to understand whether this token A is asking token B, whether token B can provide something useful. By the way, it's not mentioned, you're going to see in the next slide. It will first ask itself. So that's the idea of the self-attention, okay? It will attend all the tokens in the sentence. It will attend also itself, okay? So do you have anything useful for me? The key is basically then trying to open something. So this is how you do a Google search. You write a recent iPhone release model, and then it will look for the key iPhone recent, and then it will give you the search result. So you can think of your recent iPhone releases, blah, blah, blah. That's your query. Searching for the particular words, key, iPhone and recent, those are keys, and then it will return the result. That's what we call value. It will come later. So this then basically is a dot product. How do we know that this is a dot product? That's actually in the definition. Whenever you see this notation, two vectors and one of them is transposed, it should automatically hit you that this is a dot product. Okay? So we take a dot product of these two. This is just a simple dot product, query and key. And then I get a corresponding score. So how it will look like? So I just took query A and key B, but this should happen to all of the queries and key. So how it will look like? So let's see. We're gonna get a full 2x2 matrix, okay? So query A attends to key A, query A attends to key B, okay? Similarly, vice versa. And now we have this 2x2 matrix, okay? So this is my attention matrix for this particular sentence. So let's say I have a sentence with two words, I go. So I is token A and go is token B. This is my attention matrix. This is how it exactly works. Okay, so after we take this multiplication, so we can look back why it is 2x2. So let's say let's go back. So we have Q and K. So Q dimension was L times dk. K dimension is same. It's created exactly the same way as Q. So now I'm gonna go Q and K transpose. So L times dk. If I take a transpose, so this becomes dk times L. Okay, dk and dk cancels out. This matrix will always be a square matrix. Okay. So this QK transpose, this is always a square matrix. So that's what is written over there, L times L. Look at this. That should also make sense. What is that L? That L is the length of the token. So I'm going to get an attention matrix for the number of tokens that I have. That should make sense. So what is that? So let's say I have this. I have a cute black cat, okay? So every word or every token should equal to the other. So I must get a square matrix of length of the sequence so that I know how much one token attends to other, okay? I attends to I with some number, I attends to have with some number, have attends to I, blah, 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 okay? So this is bidirectional attention, okay? I have a cute black cat. When I'm speaking, I speak like this. Transformer, they don't know it. They are calculating attention from all directions, okay? Just like we have A times B, if let's say I grow, A times B, we also have an attention, B times A. Transformer will also calculate, grow I, okay? This is bidirectional attention. Don't care about numbers. So now we have this extra column, sigma. That sigma is essentially the softmax. We discussed in the second class. Softmax. Make sure that once we take the summation, that becomes 1. So softmax is something like, let's say, e to the power of z divided by summation of e to the z. So this summation ensures that this denominator is always 1. So when I sum them up, they will become 1. Okay? That's it. So we have this now very cool attention matrix. That's the idea. Given a sentence, given a block of code, however way it decides to tokenize, it gets the corresponding embedding, and then every token should attend to every other token. That's it. So that's basically attention matrix. And that's the idea of self-attention. So any question if you have trouble on visualizing this?
Trouble visualizing it, but this like fifth time I'm listening to it, I'm probably starting to understand it. But
Okay.
if you feel lost on the fifth time, it will start making sense. After embedded, it's all very clear and all very natural. Once you start moving to all the key value pairs, it stops being that intuitive. This is normal.
Yes, I agree. I agree. Specifically, once you try to write the code, it could be a bit difficult, but we'll come to the code soon. Okay, so we started like this, okay? Query asks, do you have something useful? Key, here is what can I offer? By the way, remember this, that this thing, this attention matrix should be a square matrix that represents the length of the sequence, the length of the token, whatever you are given. Okay, now we can come to value, okay? So value is basically, you can think of as like a carrier. So we get this attention weight calculated in a matrix. Value is what will be carried forward, okay? So I have this square matrix, L by L, Q times KT, okay? Value is another matrix multiplication. That is basically L times another dimension, dV. These are basically defined by me. L is the length of sequence, okay? That depends on whatever sentence I give. That's flexible. dk that appeared before, where was that? For the Q matrix, when we discussed this. That is dk, and now for value matrix, we have this dimension dV. These are defined by me. Okay, so now eventually what we will get is the final product. That's my final attention matrix. Of course, if I multiply L times L, L times dV, we're going to get an L times dV matrix. And that's the final attention matrix. That's it. Self-attention is basically trying to understand how every token interacts with all other token. And value is something like that's carrying forward. Whatever I understood, it's trying to carry forward. Yeah. So from now, we can move from semantics to contextual understanding. Okay. There's another thing that was introduced on the paper, not only self-attention, but the multi-head attention. So multi-head attention is basically, you can think of self-attention. You see the scaled dot product attention? So scaled is because it's scaled by this number, square root of dk. It's like a variance scaling. Dot product because it's qkt. Okay. So scaled dot product attention. That's this. Okay. We have several of those. That's why it's written with 8. So that's the idea of the multi-head attention. Okay, then we have this very weird looking equation. Not so difficult. You look at. So What is this head? Head is basically calculating attention. Attention at every one of those heads. And then I do a concatenation. You will see concatenation. What does it mean? I have some nice images here. Okay, so usually let's say when we define all the time I always took those dimensions because those were used in the original paper. So we start off with some sequence times embedding matrix dimension, that's we call D model. Now, let's say I have 8 attention head. What we discussed, we can think of that as only one attention head. Now we're going to go to multi-attention head. Depending on that, I can get this decay. So when we define the model, when we are defining the transformer network, we only care about the embedding matrix dimension and the number of attention head. Everything else will slowly fall into place. Okay, then initializing now for those heads, we initialize a corresponding weight matrix. And once we multiply this W and X, W times X, we're going to get this L times DK, okay? So L times D model times DK, so D model cancels out. We are left with L times DK. So how do you actually think about this? You can think about this as something like, let's say we just think about the query. So X times W, this is the learned weight matrix. We're going to backpropagate and we will learn these numbers in this matrix. This is what we get, okay? We're going to get corresponding key and value, and we will calculate corresponding attention for that particular head. We will have 8 of those. We're going to have 8 of those heads, and we concatenate them, okay? So concatenate, when we mention concatenate, so let's say I have an image with size 32 times 1. And I have another image, same 32, 1. So when we say concatenate, we always think about concatenate by the last dimension. So this will become 32 times 3. This is default. So if you just write np numpy.concatenate, it will always do by the last axis until and unless you specify something else, okay? So how we implement, so this is how you can think of this, very simple. We calculate query P and vectors separately, and then we just add them up, concatenate them up. How we implement in code, we're gonna see the code soon. So we have input, we make 3 copies of those inputs. They become my query, key, and vector, okay? We multiply with this WQ, WK, and WV, learnable matrix. We get the corresponding ones. At this point, we break them down, okay? What we have here, we have broken them down. So you remember that we started with 512 embedded dimension. And I have 8 heads, okay? So every one of them is 64 length matrix. So 64 times 8, that is the dimension of the embedding, 512. We do the same for all, okay? Key and values. The idea here is that they give a beautiful explanation in the paper. The idea is that you can think about those different heads. So what is on the L? L is the full sentence, okay? You can think about these different heads. They're trying to capture different meanings, okay? Maybe one is trying to understand the relation between the words. Maybe other is trying to understand how the first word is really related to the verb, etc. How the adjective relates to the noun, etc. So those are the idea of the different heads, trying to even go deeper in understanding, okay? Once we have this, query key and vector separately, we have the corresponding attention head calculated, H1 to H8. And then we concatenate. So we have this L times 8 times DK. So H is the number of heads, 8 heads, and decay, those dimensions, okay? So I have this decay length as like a column vector, and I have 8 heads, and L was already there. L is the length of the sequence. So that's my full dimension. What is the WO? WO is the final matrix. If you go back to that equation, so I have head 1 to head 8, then finally I multiply that with WO. Where is that? Where is that? Yeah. WO dimension is basically the embedding model dimension. So H times dk, H was 8 heads, dk is 64. So that is 512 times 512. Make a product from H to W0. So I'm gonna get H times dk will cancel out. So I have L times H times dk. H times dk is D model. So look at the input and the output. Input was the semantic understanding, the output, the contextual understanding. Super cool. The dimension is the same. It has to match. Okay. In between, we had this L cross L matrix, which was every token trying to understand every other token. Then we do some processing, blah, 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 blah. Then eventually we come to the same dimensional matrix. But this matrix is now way more enriched. This matrix now knows, hopefully, contextual understanding of the sentence or whatever, a big code, okay? If you read the paper after this, then it should be way more easier. So we have WQ, set of real numbers with those dimensions, D model times dk, and corresponding K and V. And how do we employ? We employ 8 parallel heads, and for each of them, we have 512 embedding dimension. So D model is 512 divided by 8, we have 64. So again, this column is 64, and this column is the length of L, and the decay is 64. And then we calculate separately Q, K, and V, get the corresponding heads, and concatenate. How does it actually was? We're gonna take a break soon. This is just to go over the understanding, and then we're gonna check the code. Okay. So how it was initially introduced? Initially, it was introduced for translation. So the original transformer paper was mostly focused on translation. This was a huge problem, not a problem anymore. So we give some sentence, let's say in English, okay? So that goes through the encoder, okay? You see that now we go back to the we call the circuit or network. So we have inputs, then we have the embedding, give the corresponding positional embedding. We have the multi-head attention, then a simple deep neural net, feed-forward network, then some normalization, and then this is going to the decoder. The decoder is basically an extended version of encoder with one difference. Instead of multi-head, I have a masked multi-head. I will come to this. We'll come to the decoder part soon. But how does it work? So we give a input. So let's say I love cats. And then we prepare a data set, something like this. So you see that this decoder input at the beginning is going in with shifted right. So what does that shifted right means? So let's say I give English and Japanese. This is my data set. So I want to learn a translation of English to Japanese. Okay. So I have cats, and the input to the decoder will be sequential. What you see on that square bracket. So always the tokens will be written like this: DOS, something, and then EOS. This is very common representation. Beginning of string, end of string. Okay. So that DOS has a corresponding token. I don't know what is that token. I don't know. Let's say 78. Let's say EOS has 89. Whatever, something. It has some token assigned. Every sentence will have a corresponding DOS and EOS. Okay. So the decoder input will be shifted right. You will see exactly how does it work. So target is one by one correct prediction of the word. Okay, so that Japanese thing is translates as watashi wa neko ga suki desu. Okay, you're gonna see how it works. So how it goes, position by position. So input first goes beginning of string. So once we give the beginning of string, what I'm expecting is that it should predict watashi wa. So beginning of string goes in the input. What I'm expecting that it should predict watashi wa. Okay. By the way, this English and Japanese is a peculiar translation because so I love cats. It translates to so this is what Nico girls would be this. So this is me, cat, love, state. Okay. If I literally translate, but the big problem is this. So I have I love cat, but here it goes I cat love. Okay. So this has changed order. So you can make a guess that when we start the training, this would be terrible translation, okay? This would be all over the place. But because of attention, just like the encoder, the decoder is also seeing the same thing in Japanese. So it will try to attend and then try to relate with the input. And that's how it will learn. So ordering now is irrelevant because it has learned the contextual meaning. Okay, that's why we spend so much time on the ordering and contextual understanding. In English, it's okay, but when I go to Japanese, the ordering has changed, but the contextual understanding should remain the same. So I give the beginning of string, predicts watashi wa, then token by token. So then it goes beginning of string and watashi wa, which is passed through this. Then it should predict at that point neko, neko ga, okay, cat. Then beginning of string watashi wa neko ga, and then it should predict suki desu. Okay. So this at the beginning is going to be terrible. It will take some time. After a few epochs, it's going to get very good. These types of problems are solved. Yeah, eventually it will end with the full stop. So full stop is this end of string token. So we can actually model this as an autoregressive model because this is happening one token at a time. This we can model this as a probabilistic model. So predict YT. Now we are really bringing this T here because now it's like a time or positional based prediction. Given all the tokens before T and the input English sentence, okay? Input English sentence, all the tokens before the current token should be able to predict the current token, okay? So that's the probabilistic model. So ChatGPT works exactly like that. It predicts one token at a time. It processes one token at a time and it predicts one token at a time. So when I say it processes one token at a time, it's just for the decoder part, okay? Of course, it has seen the whole sentence, understood the contextual meaning, processing one by one, but it understood the whole contextual meaning. Okay. So the difference is this masked multi-head. So let's take a break on the coding side. I just wanted to show you because initially when I was preparing the lecture, I was like, okay, I should give the transformer code, but I don't know how many of you are using Gemini or Google Colab. I recently discovered this with Sanya because we are working together, and then so let's go to Google Colab. Yes.
They are not one token per euro, no?
Yes,
So
you can think of this. This is like broken down into subgroups. So it is still going as like one token per time. So if you think of, let's say, this Suki des is like the whole thing as light. But this, if you break it down, it would sound like Suki and des. I don't know how the tokenization is done, okay? So you will define when you write the model what type of tokenizer you want to use. This is a pre-trained tokenizer, okay? You just load into your model and it will do the tokenizer. And then you can check, okay, what's the corresponding token for Suki Des? Maybe it has 3 tokens, maybe 5 tokens, okay? I don't know. So let's check this because this was so cool to discover. So I don't know how many, by the way, check this presentation by Mario on Claude. It turned out that I was just telling Sanya that even in astrophysics, it turned out that only me, Alex, and Gabby uses Claude Code, which is strange, insane. I couldn't believe that people were so surprised. So maybe you would be surprised seeing this. I don't know. Okay, let's go to this one. Let's create a notebook, okay? Just from the scratch because this is getting insane. Now within Colab, you have Gemini for free. I don't know how is this free, but okay. This is free, so we can use it. So let's say we start a notebook. I will try to summarize, okay? So now let's say you go home and you didn't understand nothing, okay? So you want to go to Gemini, okay? So let's try to write at least what I remember from the class, okay? Let's try to write. Okay, let's see this. This is insane. Okay, I want some help from help for self-attention. So let's say briefly what I remember is that uh, I had some sentence. I had some sentence. Okay. Then I come to token. Then I come to embedded. Okay. Then I directly went to some input. So my input was something like length of my sentence times the embedding dimension. So the embedding. I don't remember anything else. Okay. We can just start from here. So this is the length of the line. So let's say I love flat. Okay. That's L. And the embed is, I don't know, 512. That's what was written in the paper. So let's start with that. So I have an input embedding matrix, okay, of dimension L. I can put what I understood. L is the sequence length and some embedding dimension. Then I have Q, K, and V. I forgot what the hell is Q, K, and V, okay? I don't know. Then I have Q, K, and V, okay? I remember, where is my full stop? Okay. By the way, you see this? This is terrible typing. We have 2 comma, 1 full stop. So we should answer this question by Anastasia. How does it understand? Okay. It will be clear soon. So then I have QKB. I remember the boring instructor uh, there was this attention matrix. At least I remember this QK transpose T. This, I think it should hit your head because this QKT should have, if this is my sentence, this should have 3 by 3 dimension because every token should learn to attend to every other token. I love cat. I love cat. So this is 3 by 3. So this QKT should have dimension L by L. All I remember is this, okay? Now, can you please write? Okay, I always tell in the class that somehow learn to use this because this is so good. This should be taught in every class that you could use this. Oh my God, look at this. We have a markdown explaining things. My goodness. Should I teach anymore or we should go home? I guess we can go home now. Look at this. This Q has L times dk. Where is our lecture? Let's go back. Pay just a little bit attention. What exactly is done? And remaining things, where was that? Q has L times dk, okay? Oh, the attention scores are L times L. That's an attention score matrix. Scaling, you can ask why they do the scaling. I never explained. Now you have an explanation. The scaling is because you have this dot product. This dot product can increase very fast. So we scale it with the variance of the length of the vector. But that's just a normalization effect. Oh my God. It loaded Torch. Torch is PyTorch. Okay? PyTorch is like TensorFlow. It's like a deep learning library. So we can do, let's say we can do accept and run. Okay. So you can mention, okay, I don't understand Torch. Maybe I don't know. How many of you are using Torch? Yeah. Would you please use NumPy? Same as before, but just the code, okay? Okay, so now we have dimension. So let's say sequence length is L. Let's see if it matches our understanding. Sequence length is L. Okay, next code, we're going to see it just a bit later, okay? Sequence length is L. Embedding dimension is 10 QKV. That's the corresponding matrix dimension of those arbitrarily chosen, dk. So now I can check if my understanding matches or not. We're going to go through the dimension. It will perfectly match. No need to check now. And if you don't understand torch, you have a NumPy code. So this should be easier. So use this, okay? You can use this for the whole course. You can go back to all the lectures. You have the, let's say, the lecture open on the side, the slides open on the side, and you have the Gemini open on the side.
And then you just go overboard. This is terrible way of studying by opening everything on the side.
No. Just a slide and just Google Gemini. When you are drinking coffee in the morning, you can just, let me just review for 10 minutes. It's amazing. It's amazing. Yeah. We will come back to this that I was just telling Gabby. Okay. If we still have job next year and if we have the course going, we can go in some more detail with agents. Okay. For the course. Okay. So that sorry. So that was just to check that you can always come back, write whatever you understood. And you see, no, I'm still here. But this one is not shared. Yeah. Sure. Yeah. This one is not shared. Yeah. I mean, this was just to mention that the amount of resources that we have now for free, this is insanely cool for students, no? Because, like, let's say when I was 15 or 18, I only wish I had this, even during my PhD. Everybody should get a degree, don't you think? That an extra degree that we finished our PhD before ChatGPT. What? How much time I spent on debugging my code? Give me back my time, please. Please. Oh my God. So, but also I feel so powerful, and I think a lot of people will take this negative, blah, blah, blah. But I'm very positive. So just take this as a positive sign that you could build things, you could learn things that were almost impossible. before. It could go in different field within a year or two. But just by going back and forth, if you have really good ethics on studying, good habits, this is insane. This is absolutely amazing. Okay, let's get back to the presentation. We're going to finish with the multi-head and then that's it. Masked multi-head. That's the only slide remaining. Yeah, sharing back. Yes, okay. Can you see, right? You can see, right? Yeah. Can you see the slides? You stop?
Yes, we can. Now I can see. Thank you.
Okay, cool. Perfect. Okay, good. Okay, so let's just end with this, then we take a break. We should take a break at 3, right, Cecil? We have the class. Okay. No, not class, a meeting. Okay, let's go back. We're gonna finish in 6-7 minutes. What's the difference with the multi-head attention and masked multi-head attention? And that should give you an idea exactly how ChatGPT works. Because ChatGPT works only on the decoder side of the model. So one more time, attention, remember this as matrix multiplication, dot product, finding interrelation between different tokens. Then multi-head attention is basically trying to understand different parts, not only just attention between different tokens, but also some other types of meanings, how nouns and verbs, they correlate, how different words in different languages, they correlate, etc. So going from one to multi-head, it's like building deeper neural net with many parameters. Many parameters means more complexity and more meaningful things should come out. That would be discussed also in this lecture at the end when we finish. Okay, right. So this was multi-head. We discussed the training. So training is one token at a time and then predict one token at a time. That's the input. And the output is also one prediction of token at a time. Okay, so this extra thing, masked. What does it mean? So the idea of the masking is that once you try to predict the token, so let's say before, in the encoder side, it learns the whole semantic meaning. I love cat. Cat also looks back at I. Cat also looks back at love. So it's the full attention matrix. Masked attention matrix is just looking up to the current position. Okay, so if we want to predict token at position T, we should not be able to see anything beyond T. If I want to predict I love and then comes cat, I shouldn't be able to see what comes after I love. It could be dog, blah. The model should learn, given the context, okay? If I'm talking about dogs on the previous paragraph, hopefully it will not be a cat. That's the idea. So GPT uses a decoder-only model. So now here we can go to ChatGPT. How does it work? Now here something should hit you, right? So we say ChatGPT uses only decoder side. What was the encoder side? If we go back to the network, so let's go back to the training loop. So the way we think about the training loop as like conditional probability. So the encoder side is taking the corresponding input. So inputs in English and etc. Okay, whatever, many English sentences. And then the decoder is trying to predict the corresponding Japanese words, if we think about the translation. So if we just focus on the decoder, this X as what is going on the encoder. That's the corresponding input English sentence. Okay? So if I don't have the encoder, basically I shifted this X to 0. It doesn't exist. Okay? So now I have my new equation just to predict YT given all the tokens before T. That's what is done on ChatGPT. It's not trained on X and Y pair. Encoder, decoder, original transformer, we have X, English sentence, Y, corresponding Japanese sentence. We are trying to predict the tokens and then we compare. ChatGPT doesn't have any X. It only have the whole English language from the whole internet, okay? And this uses masked attention. We just don't do supervision anymore. When we have an XY pair, we are trying to predict Y dash. We compare Y and Y dash, true and predicted. Now, I can think of this. Let's see why we can write this as X. Try to predict token at time t given all the token before. No supervision. So ChatGPT is a self-supervision model. Okay, it somehow learns without any training objective. And that's the idea. So that's basically Anastasia's question's answer. You scour through the whole internet. The internet contains tons of garbage with many typos. And just by masking, without any supervision, it learns automatically. Insanely cool, okay? Insanely cool. Yes.
Fine.
Yes.
See that there's no more literal now.
Yes, it's actually a big question in the company. So usually, so you will go away, but anyway, and then let the part have a break. So what the companies they show will come just soon. So once we scale the model, both model size and data, the performance somehow improves. So now we are hitting the boundary of the scaling law, specifically with the data. So they try to curate the data. They are now building model-specific tasks, something like, let's say, mathematics special GPT or philosophy special GPT. The data is actually the biggest problem. Of course, you see the data center and blah, 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 etc. It's a big trouble with the data when we will hit the data ceiling. It's almost we hit the data ceiling, but can we actually use the generative models like let's say ChatGPT to generate reliable data? Big trouble, okay? So it's on the edge of the scaling law. You're going to see the scaling law later on. Okay, so before we had this type of matrix, so Black Cat could see I have what we have now, masked attention. So positions I should not be able to see position J if J is lying at a higher position than I. This is my full attention matrix. If I goes in to the network, you see that now there is no Japanese. Let's say I just create a GPT English GPT, only English words, okay, through the whole interface. So now I have a sentence like this in a book somewhere, okay? So I have a cube black cat. So when the model is processing I, it should not see anything else, okay? Then it predicts have after a lot of training, maybe I have, then it should not see a cute black cat, okay? Then it predicts I have it should not see. So that's how we create this masked attention, okay? So the attention matrix is now masked. So the model should be able to predict what's going on. And that's the equation. So we have the QKT corresponding matrix, but we have this very weird notation with this complex matrix. So this is Cij. So for position I and J, I have the original one, original attention matrix value only when I is less than J. Every other time is minus infinity. Why it's minus infinity? Because if you go back, how do we actually apply this? We apply this with a very cool function. What is that function? Do you remember? Softmax. Okay, somebody said. Okay, good. Thank you. I don't need to go back. Okay, so softmax is e to the z divided by sum over the z. So everything else here becomes 0. Okay, so setting it up to minus infinity and applying softmax will make it 0. So I only see the corresponding token, learn the token via embedding, and then everything else is 0. I predict the next one, everything else is 0. Okay, and it continues. That's it. Okay, so I think we can take a break here. Let's finish this slide. the loss in the training. How do we do this? You have an idea. So we want to predict YT. I know what is exactly YT given the tokens up to the time before T. So we're going to compare the true token and the predicted token. Okay. So this is just a simple classification loss. This is just simple cross entropy loss. Go back to first class again when we discussed multi-class classification. So how do we think about this classification loss? So it's running over from I1 to Z over the whole vocabulary. So I have 57, let's say in ChatGPT 2, I have 57,000 vocabulary. So it's gonna predict the 57,000 numbers, okay? 0 0.03, 0 0.08, minus 0 0.19, 57 of this, okay? These are the corresponding probabilities. And then I compare with the true one. The true one is always one because I know the corresponding true token. This is the predicted token probability. Let's say this is cat. Okay? It's time to predict cat. And the true is, I don't know, let's say dog. Then I'm going to compare. So for dog, I have a token, a corresponding learned token. And then I compare with this. This is just a simple classification problem. Yeah, exactly. Okay, so we can come back from here. Yes, okay. So we learned over the whole internet, and during the so just to finish the training. So during the training, you give the whole data set, and it somehow learns the representation of what's happening within the data set, trying to predict the next token. When you go for inference, inference is what you are doing right now, or what we did just right now, which is in the Gemini. We give a prompt. Given the prompt, it tries to predict the corresponding useful token. The token is then fed back to the model, and then it predicts the next token. So this is an autoregressive model, happens one token at a time. Okay, we're going to come back from here, that this will lead to a foundation model. Okay, let's meet at 3:20. Yeah, okay. No worries. Going over the current models, very, very simple.
that, so that when you do it with that, it's great faster than that until checking it.
Yeah, but the question is, for example, when I was learning, I learned to check how the software works and whether there's something reasonable by doing it. And
Exactly.
very slowly. So it was like bottom-up approach. You write a function, you check it, you write a class, you check it, and then slowly you learn how it should all work. Now, this avenue is completely
Yeah.
stupid to learn this way, but how do we teach people do this other
way.
how to
Exactly.
do it?
Exactly. Yeah.
No, but I mean, I still think that there is this basically protocolar thinking that people need to learn. Because if you just pass it to the let's say Claude or GPT, everything, it will throw you back everything. But it will be at best one-time use code.
What do you mean?
Just for one problem.
What do you mean?
I mean, let's say if you build a code model by model,
Okay.
it's much easier to reproduce the code.
No.
Yeah.
No. If you look back how the developers are using Claude, it's completely reproducible, even via Claude.
Yeah, but let's say if I have some problem.
I kind of agree. The problem will happen for particular cases, no? So let's say why I say like I still have 1.5 years and not 2 months for losing job is because for particular task it's still very terrible. Specifically, let's say for
rare tasks.
Exactly. But this is just over time. When the big university people, they will join.
Yeah, but I mean, let's say for this forestry, I'm building some
Yes.
pipeline for processing. And I mean, it's quite long. And it starts, let's say, GPT Pro starts to mess up things.
Okay.
But this is about practices of software development actually, because normally with all the things that was never taught in universities to astronomers, physicists, and people like this. But this is something that computer scientists are supposed to be taught. You never work on a big project like on the whole long pipeline.
Yeah.
Like highly modular.
Exactly.
And it is testable model by model and then as integration.
Exactly, but that's what I said. So
Even with model by model, yeah, that's what you think.
you basically you must think in that way.
Yes,
when
exactly.
working.
Yes.
So you must not dump all
Yes.
project.
No, for sure, no.
But
Yeah.
if you are building model by model,
Yes.
this way of thinking, right?
Yes.
For sure. I agree.
But it is very important to teach people how to think this way
Yes.
from the beginning, which is not something that we ever done.
Okay, let's begin. Yeah, we can, I mean, I hope the university discusses this. We were discussing this with Egon for the teaching. We were discussing also for the bigger universities, like what will happen to Ljubljana. Because, like, let's say we got there was a not on this quarterly report, but almost every quarterly report from 2025, like people graduating from MIT, Harvard, they cannot get a job. So even for them, no, it's a big difficulty. Imagine, like, let's say if you finish your PhD and then if you don't get a postdoc, it would be insanely difficult to get a job. No, I mean, I was just telling in the group. So after my PhD, 2019. Yeah, so basically 18, I submitted everything is done. So I applied 3 jobs, all AI researcher, okay? I have my PhD on astrophysics. No background on AI, okay? Just some projects. And I got 2 reply back with 1 job offer, okay? So this year I signed the permanent position for the university, okay? So this happened after they asked me like 3 times. So Finally, I signed. So I was telling in the group, the reason I signed is because I don't think if I get, let's say I leave now, I will not be confident at all to land a job in 1 year. Forget about 2 months, 3 months, I take a 2 months break. It would be terrible. It would be terrible. I mean, and that's why I feel sad. I mean, let's say I don't feel sad for me because let's say at least I lived my 20s, no? But we should think about the next generation. Like it really bothers me that there is no discussion in university level, no discussion in parliament level, and it will hit like a wave, like a tsunami. It's already hitting. It's already hitting, but it's not mass layoff yet. Everywhere. It's just some sectors are slowly completely going off, and people are just complaining online. No? But yeah. Okay, let's begin because we will come. Maybe we can touch upon it at the end. Okay. So let's see if the mic is on. Yeah. Okay. Good. Istok, you can still hear, right?
Yeah, still here and
Good.
hearing.
Okay.
Thank you.
Okay. So now we're going to slowly jump to concept foundation model. So we discussed this on the last class very shortly. So for diffusion, when we generate image, we discuss the foundation model as where we can combine different types of data. So we write a text and then it gives me an image. So let's say I go to write on ChatGPT or Gemini some description of an image and that will give me a very realistic image. So that's a multimodal analysis system. So I have text and image directly processed at the same time. So we're going to think about another way to learn about foundation model. So here, we'll specifically come to foundation model definition. But here, so let's say if we think about GPT, so
Sorry,
basically the idea
sharing
is
the
that
screen?
you upload the whole internet data and then it just learn to predict the next token. That's all it's basically doing. So trying to predict YT given all the tokens before flying T, and then I compare it with the real token. So real token is this, predict the token with this, and then I just calculate loss. Okay. So no objective.
Sorry, share screening? Is it?
Yes. Oh my God, you cannot hear. Okay.
No,
Okay,
I
wait.
don't see screen.
No, because I guess when I'm moving away, you cannot hear. Okay. So for this one, it's basically a classification problem, but without any target objective. Now, without the target objective, downloading the whole internet data, it already learned not only about the whole English language syntax, it learned to reply back to some questions. The question is a pattern. It could give summary. It could write an abstract for a paper. It could give the codes. And it could also give step-by-step logic for, let's say, some puzzle-like problem. So these are learned properties. So we can think about them as something like an emergent property, okay? So what the model sees is basically just a number of tokens. So you give a block of code, so it make into small divisions, and then you have whatever subword or whatever way of tokenizing. By the way, we tokenize codes slightly differently. But anyway, let's think of them as some form of tokens. So the model takes these tokens and is trying to predict the next token, okay? So if you look at the scaling, what's happening, at least till the time we know what happened. So GPT-2 published 1024 tokens. So the context window that you can, let's say, copy paste a block of code, it cannot be, let's say, like a million lines of codes, okay? It has a very small context window. GPT-3 has twice. Now when we go to GPT-4, it has 100,000 tokens, okay? It's trying to reach 1 million tokens, both Claude and GPT. So that's the target. I think also Grok recently mentioned, Elon Musk, that all of them are trying to reach 1 million token. So basically, you can think of this as processing at the same time too many operations. So not only we have data centers, but we also need tremendous amount of compute. And the idea is that So let's go back to the training. So basically, we don't give it any target. It downloads all the internet data and it somehow learns all of the things, okay? It learns the pattern of some physics questions, chemistry, material science, atmospheric physics. It somehow learned, okay? Give some questions, give most of the time now, at least reliably good answer, generating code, etc., etc. So without any target, it already did all of these things. Now, I won't mention here, but now let's say particular dedicated models, something like, let's say, very recently, Google released this model called, I think it's called Atlassian. It solves only mathematics PhD level problems. So they were fine-tuned. I will never discuss fine-tuning. We're going to only discuss something else. So this was just to mention. We are now getting some distilled version of the big model dedicated to particular task. And this dedicated task is done via fine-tuning. We'll not discuss fine-tuning at all. We're going to discuss something else. So first point here is that we are heading towards insane compute demand. I guess we know this from the GPU prices. So what we'll discuss is this beautiful GPT-3 paper, okay? Back when OpenAI was open, so we knew what was going on. So this paper, no, it's not like attention. It only has 70,000, 80,000 citations, let's say. So this paper was basically describing GPT-3 in 2020, okay? So GPT-3 model that was released was kind of based on this, but the paper came out, you see, it's on July 2020. And by the way, back in 2020, I didn't know about this paper. Okay? I just knew about transformer back then because I'm catching up. Okay? I cannot catch up anymore what's going on in AI because every day there is a new paper, even though I try to read a lot. Okay, so this paper, you see the title. So language models are few shot learners. So it's saying something about few shot, and then it's saying that it learns something with few shot. So we want to see what is actually few shot and why it matters a lot. So basically the idea is that we have large models and tons of data, and that leads to some generalizable property, okay? Understand some physics rules, coding rules, etc. Okay? Now, what about few shot learning? So the idea of the few shot learning, or what this GPT-3 paper is saying, few shot is basically we take already existing a big model. So let's say I take a huge model for image analysis task. It is trained to do some image classification, okay? Now, on this pre-trained model, I give some examples of data that the model has never seen. So the way these models are presented, all this N-way K-shot model, okay? So I have on this new data set that the model has never seen, I have only a few examples. You're going to see on GPT-3 how many examples they use. So these examples, we call them K, and N are the number of classes. So N-way K-shot problem, okay? The model essentially learns the feature. So let's say I train a huge model of all dogs and cats, and then I give pictures of some wolves, okay? And I don't know, some birds. Only few examples. So the idea is that with this model, because the model already learned to extract features from dogs and cats, including their shapes, many other features, blah, 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 now it should be able to extract features from only these few examples, even though the model has never seen the images of wolf. So we reach to this extracted feature space. This we call embedding. This you can think of the latent space. Okay, so latent space and embedding, they're used one upon another. So when we discuss evolution, so we have image of a man, okay, then it goes through some layers, okay. Every layer, we reduce dimension of the image. So let's say we start off with 128 times 128. And then eventually we come here with something like, let's say, 256 dimension. So what it means is that I have compressed the information of 128 times 128 pixels into only 256 numbers. So this is the latent dimension. This we also call embedding in language. So that's the embedding matrix. If you think about this L times D model, so it depends on the number of dimensions of this
Sorry,
model.
can you share the screen? Share the screen online?
Wait,
Could you share the screen?
Wait. Sorry, Stock, wait just a second, because today we
Yes,
have
yeah.
the camera was working, but I can turn on the video. You would be barely able to see something.
Oh,
but okay.
okay. I see.
Yeah. So essentially we reach to this compressed space, right? So this compressed space, we can compare this with the embedding matrix, because you saw what happened. So we had this some input dimension, L times D model. That's my embedding that goes in the attention. And then comes out the same dimensional matrix, but learning this causal representation. So when we say embeddings here, for image, we are basically referring to latent space. So a large part of the this combined models, so this text and images, all of them are kind of combined in the latent space. So they're trying to interact. We never discussed this in the class very detailed. But this is a model called CLIP. CLIP was basically used for this DALI 2 or image generation. So you compare the vector representation of the image and the corresponding vector representation of the text. So when we say embedding here, you can always think of this as like the text embedding matrix or the latent space vectors. It's a compressed information that contains very rich information. Even though it's compressed, but it's very rich. So the idea here is that this few shot learning, then we can cluster things together. So let's say then this dogs and wolves will be clustered together and the birds will be thrown farther away in a space of clustering. So even though the model have never seen this n classes, whatever, number 3, number 4, I don't know how many number of classes, the model is still be able to classify them. So the way we think about this is something like, I got this from the IBM page, very nicely written, so you can actually check. So let's say I already use a pre-training data set, and then I have only 3 classes. So fish, some sheep, and then some bees, okay? And I have this, sorry, I have this 2 examples and 3 classes, right? So this anyway, K shot, okay? So K shot is only 2 examples. So I now do pass these examples. So no training, okay? So when we say training, it basically means we perform some backpropagation or do some gradient update. We change the weight of the model. No training, nothing. We just pass these examples, and just from the feature extraction, the model would be able to classify them, because the model has already learned, without seeing any of the examples before, what features to extract, and it could already classify this. This is a very cool concept. We started from a big trained model. The model is insanely rich. Then we pass some examples that it has never seen, and it will keep the examples that are close by together farther away. They will examples that are farther away, they will put them farther away. And then we can assign classes 0 or 1. So let's say this wolf class would be, let's say, class 1, and bird would be class 0. So that's the idea of the few shot learning. We say learning, but no learning is happening. So when we say deep learning, the term deep learning came basically from backpropagation or weight update. It's a few shot learning, but there is not actually any learning. It's just understanding the embeddings even better, okay? So again, this is from GPT-3, such a beautiful paper, okay? You can read back again. So here they explain. So with images, it's very easy to understand, but even with the text, the way they presented in the paper is so easy to understand. So what we used to do before is this part. This part is called fine tuning. So we train a model, big model, Then we take some example data set. So let's say we can go back to the images. So we train a model with dogs and cats, and then we give some examples of fish. And then we, let's say fish and sheep, and then we train the final few layers of the network. This is called fine tuning. So this is what was used to target. So let's say I train GPT-2 by doing this next token prediction. Now, I don't know whether downloading the whole internet, it will learn the translation from English to French. Now, I prepare a separate data set with examples of English and French. And then I fine-tune the model, okay? The final few layers, I fine-tune. And then I could use this model. This paper, it shows that we don't need fine-tuning anymore. Just by scaling the model, it's good enough that it will learn the task. This was the most pivotal paper, 2020, 21, 22. It was one of the most pivotal papers. So now what we do is this, left-hand side. Right-hand side, what we used to do before, fine-tuning. Left-hand side is what we do. We train a huge model, and then we try these different shot techniques. So zero shot is we don't pass any example. So few shot is what we describe. We try to give few examples so that the network network at least get some extracted features from these images and then compare with the query set where the features fall. Whether the extracted features of B fall close to this picture or whether the extracted features of sheep fall close to this one. So that's the idea. No learning. And that was what they showed for GPT-3. So give some examples of, let's say, C author and then corresponding French translation, few shot, and then it will automatically be predicting what's the corresponding French translation for T's. Then they also tried one shot, only one example, and zero shot, no examples. Only increasing the model size, they could do this. So this was the big result from the paper. This paper gave highlighted this law called scaling law. And it's so well written. We used to do before traditional fine-tuning, right-hand side. We don't need no more fine-tuning. We don't need no compute after we train the model for some particular task. So that is the idea of the foundation model. We train a big model. Somehow, the model learns things that it were not trained. The model is not trained to do anything, but it just learned. These properties are emergent properties. Okay, these are generalizable properties. That's the debate starting, okay? Whether we have reached AGI or not, artificial general intelligence, okay? In my mind, we already reached because we can, the models can interpolate between physics, chemistry, math, biology. It was never learned to do any of those tasks. It just learned from the data itself. So these are the two most important plots, along with another one. We'll come back to that later. So what they show here is that on the x-axis, the number of parameters in the model. So at least we know that GPT-3 uses 175 billion parameters, okay? So that's the GPT-3 Pro. So what they show is that when we increase the size of the model, the performance, so the K is 64. So we have 64 examples for this particular task. It's a trivia. So you ask something like from Wikipedia, what would happen on this 1987, 3rd December if you go back? Some historical event happened and it will say something, okay? So that's the data set. This Lambada is basically trying to go back and forth as like a debate to form some logic. Okay? And then we compare the human performance level. So what you see here is that when we increase the number of parameters, without any training, with only few examples, the model accuracy always increases. This is insane. After this paper, everybody's tried to scale their model. Okay, so the scaling comes from here. This huge demand for data center, it kind of started from here. This paper was like a pivotal paper that showed, okay, we can basically scale our model and that's it. We don't need to worry about anything. The model would somehow learn about weird properties that it was never trained on. Okay? Across many different tasks. These were only two examples, but there are many plots like this. So zero shot, no examples. One shot, few shot, all of them increases with increasing the model size, but the few shot one, by showing few examples, it increases massively. So if you think about this, when we go back to this image example, that's why it was so easy to understand. Basically, extract features from, let's say, this bee that it has never seen. It has never, the model has never seen no bee, no ship, no fish. It extracted features, and then it's comparing the feature vector of the bee and this corresponding image, and they fall together. That's how they assign the class. So it's basically like learning the properties, even though it was not trained to do that particular task. Very cool. Then they publish this dedicated paper for scaling laws. Of course, this is now highlighted in every company, every talk, everywhere. So written along with OpenAI, but also a researcher from JHU. So scaling laws for neural language models. You probably know a few people, especially this one, Dario Amore. We have Claude, okay? So that's his company, Anthropic. He left in 2020. Okay, so here's the abstract. Just the two highlighted part basically tells you the whole thing about the paper. Empirical scaling laws for language model performance across the cross-entropy laws. So cross-entropy laws is that one. We compare the predicted token from the model to this token, okay? So the law scales as power law with model size, dataset size, and amount of compute. So the loss basically goes down. It doesn't matter what we increase, either the model size or the dataset size or the amount of compute, okay? With some trains spanning more than 7 orders of magnitude. You could probably see here. We started from something like, let's say, 100 million parameters, and then we increased 2 orders of magnitude to 100 billion parameters. Okay? Here is the final conclusion, only 6-line abstract. Larger models are significantly more sample efficient. We will come to what does that mean, sample efficient? Such that optimally compute efficient training involves very large models or relatively modest amount of data. This is super cool. We'll try to explain what's happening here. Training involves, sample efficient training involves very large models on a relatively modest amount of data and stopping significantly before convergence. When we train a network, we usually use for loss as a function of epoch. We stop when the validation loss doesn't improve. It kind of saturates. We stop the training here. No need to train more. Okay, we just stop here. It's saying that we don't need to wait for the convergence. We can stop significantly before. Wow. This is like contradictory to machine learning ideas. So let's see what's going on. So sample efficiency. So the idea of the sample efficiency is that if I make my model bigger, I need less data. Okay. So somehow we think of now, we are slowly now going from a model to a brain. So if I have a bigger brain, somehow I need less and less data. Okay. You train your dog, you need to give like 10 examples and 20 treats to do one trick. Okay. With human, yeah, one slap is good enough. Okay. No, it can love them. Okay. So that's the idea. Okay. It's a joke, but okay, that's the idea. So to reach, so this is how actually it was presented. So we can go to a smarter model, this bigger brain model. It's faster to train a huge model rather than use a lot of data and train a small model for longer time. So that's the sample efficient. Why? We have to stop this training before convergence. And this was another big point now on training. That's the law of diminishing return. We are actually hitting this phase. Very, we are almost at the border of this. So when we approach this accuracy, high accuracy or low loss, it will reach this plateau. So let's say we have some loss 0.01. And here we have some loss 0.008. Okay, they're very close by. But to go from 0.01 to 0.008, the updates here are very less. So we need to train a lot of epochs to go from 0.001 to 0.008 because this is flattening. It's not really changing so fast. It's changing fast here. It's not changing so fast here. So we are basically burning our compute to gain a small accuracy. So that's the law of diminishing return. So we can stop here at 0.01. We don't need to go here. For that, the idea is that it's better to spend your compute to train even bigger model on this part. Okay, rather than spend your compute on this part, you make a bigger model and spend it on here when the model is learning really fast. Here is a nice example, okay? So let's say I have in a company, in a startup, I have 1 million budget for my GPU, okay? So first approach is I train a small model, okay? Let's say, I don't know, 100 million parameters until it converges. So really the validation loss doesn't increase anymore. So it's like we can think of this as like a tiny brain, but it's perfectly optimized that type of particular task. The other approach is that we train a huge model, 20 billion parameters, and let's say stop it about 20% of the final value, okay? The idea is that this larger unfinished brain, if you think about this as brain, this model that stopped here, it's bigger, that brain will always outperform this particular small brain. Now, from here on, this idea of the brain or representing model as brain came about, that we think of making the model bigger brain, human beings, we have way many different ways to form connections. And we can learn really fast rather than a particular model trained for some specific task, okay? So these were the 3 plots from the paper. So what you see here is this test loss that's going down with compute size, test loss going down with the dataset size, number of tokens, dataset that's that loss that's going down with the number of parameters. Okay, so we know number of parameters. So non-embedding, because embedding matrix is fixed by this dimension, L times D model. So when they say this non-embedding parameters, so non-embedding parameters are the parameters for key, age, V, and the feed-forward network. So if you go back to the transformer, so all of this model uses transformer, the decoder part. So let's go back to the decoder. So yeah, so we have this fixed embedding matrix. So when they say non-embedding, so this is already fixed. So this is already fixed, L times D model, 512, 1024, whatever. Parameters are coming from here, masked multi-head. So we have Q, K, and V matrix, and then we have feed-forward network, a dense network. So when they say non-embedding parameters, that's what they mean. Okay? We have a fixed embedding matrix, and then we train everything else. Let's go back. So for all of the cases, the test loss goes down as we increase the compute, we increase the dataset size, parameters. Okay, so that was that point. That was the first point on the abstract. It decreases, the cross entropy loss decreases as a power law. That's the scaling law. As a power law, irrespective of the model size, dataset size, and the amount of compute. Now, this amount of compute, when we write papers now, we must mention, we use a big model, this quantity. That's called the petaflop per days, okay? So how many petaflop I use in a day? So you see that that's what they mentioned, sometimes varies over 7th or 10th order of magnitude. So that's this one, 10 to the minus 9 petaflop per day to 10 to the 1. So 10th order of magnitude. So what's a petaflop? So peta is, of course, 10 to the 15. 1 day, number of seconds, 86,000 seconds, and then I multiply with this. So that's the number of operation, okay? So in 1 day, it's doing this 10 to the 19 operation. One person will do 1 calculation per second. Calculation, basically calculating the attention matrix and the dense network matrix and the feed-forward network. So these are the number of computes. Once you know the number of parameters, you can easily calculate the number of compute because this is just matrix multiplication. One person does one calculation per second. Yeah, it will take 350 years, okay, to reach this. That's why we have GPU, and that's why we are building bigger data centers, okay. Now, another paper. So that paper was published in 2020. 2020, the main point, so they do show that increasing data size also decrease the test loss. But their main point here is that this one, that if I increase the compute, so by increasing the dataset size, I didn't gain as much. So you see that 10 to the 8 to 10 to the 9, the loss goes from 4.2 to 2.7. But look at this, 10 to the minus 9 to 10 to the 1. So this is a huge amount of compute increase, and the test loss goes down. So their main point was that let's focus on compute. Let's just build a bigger and bigger model to low this, to make this cross entropy loss lower. This paper was published in 2022 by DeepMind. They released a model called Chinchilla, and they highlight another one. Is that, okay, we scale the model, we reach better accuracy, okay? The loss is lower than the small model, great, but are they really optimal? When do I know how big the model should be? Now this model, this paper, this Chinchilla and this particular research highlights that we also need to increase the dataset size. How much dataset size? So let's see here. So this is the abstract. So large language models are significantly undertrained. That means it didn't train enough with enough data. Consequence of the recent focus on scaling language models while keeping the training data constant. So I keep the training data constant, I just increase the model size. By training over 400 language models from 70 billion to 16 billion parameters, ranging from 5 to 500 billion tokens, we found that compute optimal training, model size, number of training tokens should be scaled equally. Wow. So they then highlight that for every time I increase the model size, the dataset size has to be increased so that I could optimally use my model. So that's why they say that this other model, this ChatGPT 3, this model was severely undertrained. There's a very nice graph in the paper. You can look back at it. But this is where it comes from, this scaling loss. So model size, data, everything has to be increased, and somehow just by trying to predict the next token, we understand some things that we were never initially planned to do. Okay, super cool. Okay, so this is the idea of the foundation model. So we train a big model, GPT-3. Once it is trained, we just keep it like that. Okay, so that's why you get this reply back. Okay, our model was trained before 2025. So I cannot give you update on what happened on 2026 April, okay? So let's go with that. So we have a fixed model trained on a huge model, trained on huge amount of data. And then we can use that model for many different tasks. So that's the idea, the foundation model. We just train it without any particular task objective. And then somehow it learns to do other tasks. Instead of training for different tasks, ChatGPT can do all of these things: summarization, emotions, sentiments, etc. This is the idea, the general intelligence and emergent properties. Okay. So if you think about actually human learning, I think one of the biggest joy of learning is that keep on learning, and then at some point it hits that, let's say, the quantum mechanics is very deeply connected with material science, some particular topic, and then it's like, oh my God, I now understand it so better. So even though you were not really trying to connect them, but they somehow happened in your brain. Somehow you figured out this connection. So it's very similar. It's very similar, the way these models learn. It's the properties that they're learning, they're emergent, okay? Here I wrote only to bachelor's level, so you can solve math physics at least till bachelor's level. But yeah, I just didn't write master's level or PhD level, just so that we don't humiliate ourselves. It actually does better sometimes, master's or PhD level. Okay. Task agnostic, but we got a general purpose model. If I have a local LLM installed on my computer, I can do many, many different tasks. Some examples, we're gonna finish. So let's say LLMs are everywhere. So now it's used to train some data. Two of my colleagues actually worked on this paper, Robert and Sasha. We wrote many papers together. So they show basically you could use the principles of large language models in getting some particle events. So we have this big proton-proton collision inside. You get the events, you process them as text, and you could read event classification, etc., etc. Train them without any task, and you could do those things. So that's another point I just wanted to highlight. So we started off with text. So text as like a time series, okay? So I say something at time t, then at time t1, then at time t2, and it continues. Okay, I have my full sentence. It has a meaning from left to right. Okay, that's why we gave this example of stocks. But you can process actually anything. So it turned out that you will actually process the event tag. So proton with energy E and momentum P. Then E prime with E prime and E prime. You could process it the exact same way as you process a text, and you could get some emergent properties out of this. Of course, we have, I think the biggest example of LLMs are in drug discovery and chemistry. So this is published in Nature. So LLMs could be used as for predictive chemistry, and they gave a very nice representative image. So we have this huge data set of molecules and spectra and blah, blah, blah. You usually process them all as text. And then you have this general purpose task. They show only 3 examples. So let's say they keep this, okay, what's the transition wavelength given this thing, okay? It can predict low possibility of this, okay? The best thing I found is this one. So it can predict this isomer transition given at wavelength. It could predict the design of the molecule, okay? This is insane. This is super cool. The good thing also is that, by the way, both of these papers, the code are public because of, this is published in Nature, so the course has to be public. So you could check them out. This is also for the, I was telling this to Sandra, that I wish there are more people from the material science and chemistry, they try to apply, because I want to apply, because the data sets are, compared to astrophysics, it's so frustrating, because if I want to apply LLM, I have to completely modify my astrophysics data. So we tried this. But for material science and chemistry, you can think of these molecules or molecules as like a chain of atoms. So you could put them side by side, some smiles, strings or something, and then you can process them as text. You make the model big, you take huge amount of data, and something might work. Of course, many examples in astronomy. By the way, this paper came out 2 days before. So you can take a look. This basically reviews current examples and what we could do, blah, blah. And eventually, I guess what will happen is something like this. We're going to sit on a computer and we will type, give me a research plan and do the research, okay? So when I was in Tokyo, so few of the people from Google, they opened this company. So this is called Sakana. Sakana is a fish. The Sakana means fish in Japanese. So 2022, they published their first AI scientist paper, and this is the updated version. March 26, 2026, published in Nature. So it basically generates research idea, then writes a draft, then design the experiment, run the code, review it, give some numbers, send it back to the reader. If all this okay, if everything is okay, then the agent will submit the draft. Okay, so it was also submitted in archive via the agent. So I guess eventually we will, this is only done mostly for machine learning studies with some particular data sets, but I guess this will happen for all our research tasks. if it still exists. Yeah, so I guess things are changing insanely fast. We are on the exponent. So yeah, it's very difficult to keep track. We are not here anymore. We are not here anymore. We are somewhere here. Okay. It's like explosion of information. So I guess it's better to go with the red one. So I hope the university actually adapts more, but also individually. But then I don't know, we can go back again, have debate. Even if we adapt, what does it mean to adapt? What will happen after adapting? We don't know. Yeah. We'll come back to this. It will be only for the two people, Erin and Anastasia. But if you're writing some microcredit, you can just tell me. You just need to prepare some small project, 15, 20 minutes, and that should be good enough. What's next? I guess if the course exists, I think we should focus more on developing agentic pipeline. But I think in the meantime, you should think about automating certain parts of your analysis pipeline already. This should be your first task, especially if you're doing your PhD, postdoc, or whatever, assistant professor. Especially, let's say, final year PhD, let's say, writing a draft. I got the results, this, and this. You put it in a code, put it in a folder, and then you should have a mini agent that should be able to write a report, at least some paragraph from your plot and etc. So that you don't need to spend time doing this kind of things. They could actually do this. They could do this also within LaTeX. So if you have a LaTeX environment installed, it should be able to generate a very nice PDF, especially for physics. Yeah. If we still have jobs, we will continue to go on teaching about more on agentic framework. We are.
There are still agentic framework next year.
That's right. That's right. That's right. I guess it will continue, but it will probably be more like multimodal agents. So we have now many agents. So we have multi-agents doing similar tasks. So let's say all are writing codes, but it will be more dedicated to different types of tasks. So let's say one is writing code and the other one is really good at interpreting figures, writing a draft, and the other one is really good at sending back mail to the reviewer, etc., etc. So I guess the job would be mostly maintaining those multi-agents and take care of those things. So maybe 1.5, 2 years, okay? Because academia is way behind the company. The companies are already working like this. Yeah, the problem is that what Alex said, no? So 1 year when this course reappears again, that's basically 20 years in AI development timeline. So even though I say it could be a multimodal agent type, I don't know if that will happen. Okay? Maybe it's completely different. It's impossible to predict. I would have never predicted if I go back to 2022 that what I'm doing right now. Okay? It's crazy. It is crazy. Yeah, I cannot fathom it. Yeah, I recommend that you learn on your own in the meantime. So I think that's the best option. Keep an eye what's going on, even though it's very difficult, it's very annoying because it's information overwhelm. But go back to the previous point. I think it's better to learn analysis pipeline automation because at least if you know how to do this, maybe other people can use it. The way I think about having jobs is something like if other people can use you or not. So I think if you at least get accustomed with some of the development, you would still be usable by others. Yeah, it's very difficult to sack senior people, right? We cannot sack the boss team. Okay? So who will be sacked is me. So if I'm still useful or PhD or postdoc, okay, you will not have a job. But of course, the company CEO will have a job. So if you're still useful, it might still be okay. Yeah, I will keep updating with new materials. But of course, we will create a new page for the next year course if it happens. But keep an eye on the resource page. I will update. I haven't updated for quite a while. Yeah, so I think the most important thing is this year we didn't prepare Google Doc before the course because it happened kind of abrupt. And also so many people registered initially, so you're a bit overwhelmed, like what to do with this. Would be nice if you give some feedback. You can just tell me personally, okay, this was absolute shit, okay. We didn't like, it's okay, but give us some suggestion. How can we do better? Of course, I think we already have some ideas on preparing the next types of materials. But looking back at this, so let's say the last two classes, we actually discussed some of the most advanced topics. One is diffusion, last class, and this one is LLM. Now, here is the thing. Let's say if I look back 2 years, yeah, I don't know, 2 years, yeah, maybe just even 1.5 years or something. So I have to give you a block of code and then give you a link to some data set so that you could actually run it. Of course, I'll upload some notebooks and etc., but you could do it on your own. I think that's the biggest advantage, even though we are all scared what will happen, but we could do things on our own that were just impossible before. So yeah, I think don't forget to have fun because the few months back we had I don't know, it was somebody's birthday in the group meeting, and then we were eating cakes and some cookies, and then someone mentioned that eat the cookies and have the cake right now because later you may not have nothing. Okay, so that's a good reminder. Okay, that yeah, very difficult to predict what will happen, but I guess the only option is to keep learning. If you have some suggestions, just tell me or whoever you like, because it's actually necessary. Because I think the way I think about teaching is basically you are the customer and I have to deliver. No, I take teaching very seriously, so it's the only way I can give something back. I don't know how my research helps anybody because I'm not a doctor or a material scientist that I can create something that's astrophysics. So teaching is the best way I can give back. So you can tell me how we could actually make this more useful. What are you doing and how we could make this more specific for your particular task? Then we could give some more examples or prepare something. Okay, we end here and thank you. Yes, done.
Thank you very much for very nice lectures. Bye.